All right, so let's take a look back here. Last week, we were talking about graphing rational functions. So here's what we want. Let's take a second and let's review what we talked about, and then we've pretty much done the 3 examples we want to do. We want to see if we can see it. I am recording. Thank you for checking though. Yeah, I am. Yeah. Make sure I did that double check. So this was the first one we looked at. What did we find here? So our goal was we wanted to figure out we want to factor the top and the bottom, right? The top was easy to factor, bottom was pretty easy to factor. And we want to find, first of all, what are any values that we have to exclude from the domain? Okay, and those would be places where we get zeros of the denominator, right? We get zeros of the denominator at 5 because of that factor and at -2 because of that one. Okay, now remember, there's 2 things that could be going on there. We need to figure out what's going on at each of those locations. So what are the 2 things that could be happening at a 0 of the denominator? What's one thing?
A hole or vertical.
Okay, we could have a hole. Right now, where would we have a hole? Okay, a hole would be a shared 0 of the numerator and the denominator. So in this case, notice that we have like factors in the top and the bottom, the x plus 5, or x minus 5s. So at x equals 5, if we tried to evaluate this function at 5, we would have gotten 0 divided by 0, which tells us that's a hole. Okay, that's an indeterminate form. We know that at x equals 5, we've got a hole. If we look at the graph of the function, that doesn't look very impressive, right? If you graph it in Desmos, for example, it won't even show up, right? It just looks like a regular function, but we know that out there at x equals 5, if I try to evaluate the function at 5, it's going to tell me the function's undefined. So we denote a hole or show a hole on our sketch by just putting a little 0 in the middle of the function, just, indicating that there's one point that's gone there.
I think they should just not do that.
Well, why don't you invent a little better Desmos?
I think what they should do is, if there's one of those holes, it's not lying.
I don't know what you'd do for that. I mean, I guess you could, ideally it'd be nice maybe to be able to put it into a mode where it would show a little, it'd show a little circle there to show you there's a hole. I don't know. I mean, I've never seen any of the computer algebra systems or graphing programs. I've never seen one that does it. So there you go. There's your make a million. So then what about at x equals -2? What's going on there? Vertical asymptote, how do we know that? It's not shared. It's a unique 0 of the denominator. So if we get a unique 0 of the denominator, if I try to evaluate the function at -2, I would get some number divided by 0, right? And that tells us vertical asymptote. That is much more impressive, right? That has a major impact on the function. We get this vertical asymptote that's like this infinite wall in the function, and the wall, butts up against this, or the function butts up against this wall, and it either has to get thrown up to positive infinity or pushed down to negative infinity, right? So that changes things dramatically. In calculus, we'll say that this is what we call a removable discontinuity, and this is like calculus level stuff, but this is a removable discontinuity because all we have to do is adjust one point. Yeah, all we have to do to repair that discontinuity is add one point to the function there, which is easy to do. We would call this a non-removable discontinuity because it would require us to move an infinite number of points to repair that break in the function, right? Okay, so we figured out where the function is undefined and what's going on, and in our table, this is how we show that. In both cases, like if on the x row of my 2-row table, I'm going to write in those important places where the function's undefined, and in the y row, I would write undefined to remind me that it's undefined there. But what I think you ought to do then, what I want you to do, is up at the top of that column, you're going to either write VA, which is vertical asymptote, or hole, right? So it reminds you what exactly is going on at those places, okay? So that gives us some important information. It gave us a vertical asymptote, which is really important to the shape of the function. What about the horizontal asymptotes? Okay, so that's end behavior stuff, right? Horizontal asymptotes, if we look at our graph, they're only important when the function goes really far to the left or really far to the right. Okay? In between, they don't really have much of an impact. Like in here, the horizontal asymptote is not important, but it is out there or out there, right? So that's an issue where we want to take a limit as x approaches either positive infinity, which is way out to the right, or negative infinity, which is way out to the left. Okay? And so we did that up here, right? We took this limit of the function, which, and all we really need to think about here, when we're talking about end behavior, remember, and we've got a rational function, we know that the leading term of a polynomial is the dominant term when we have really big values of x. So all we have to consider when we're looking at the end behavior is just the ratio of the leading terms. Everything else won't even matter, right? So when we take the limit of this function as x approaches plus or minus infinity, we'll just look at the ratio of the leading terms. Well, that simplifies, doesn't it? I could cancel an x in the top and the bottom, and I get the function negative 4 over x. And then we just have to think about what's going to happen there. As x approaches plus or minus infinity, the top of the fraction is fixed, but the bottom is exploding, and so what's that do to the overall fraction if the denominator gets huge? It drives the fraction to what?
0.
To 0, right? So we know that our limit as x approaches plus or minus infinity is 0, and that gave us the horizontal asymptote at y equals 0, okay? Now we've got two asymptotes. We've got the vertical asymptote, whose equation is x equals negative 2, and we've got the horizontal asymptote, whose equation is y equals 0. And if you think about that, that really narrows down greatly what this function can do, right? You know that it's got to stick to those asymptotes as the vertical one as the function approaches negative 2, right, as we get closer to negative 2, and the horizontal one as we go far out to the left and the right. That does a lot to help us understand what the shape of this function is going to be, right? And the only other things we really need then are, well, where are the x-intercepts, right? And what's happening between the x-intercepts? Well, are there any x-intercepts on this function? X-intercepts would occur where for a rational function? Where would we look for it? Okay, where the function is 0, but where is a fraction equal to 0? When the top is 0, right? So we look for excluded values of the function where the bottom is 0. We look for x-intercepts where the top is 0. Well, in this case, the only 0 of the top is 5, but we already know that 5 is an excluded value, so we don't get any x-intercepts, do we? Right? So then all we have to do now, is we need to just pick some test points and figure out, well, what's going on with the function between all of its x-intercepts and excluded values. And in this case, there are no x-intercepts. We have excluded values at negative 2 and positive 5. So we would just check values around those and see what the sign of the function is. We're going to pick a value to the left of negative 2, like negative 10. And what we found there, if I plug negative 10 into my function, and here it is in factored form up here, which is good, right? If I plug negative 10 in, what did we get? We can just look at the factors. Well, we have a negative factor, that one would be negative, that's negative, and that's negative. So negative times negative is positive on the top, negative times negative is positive on the bottom, and we just follow our sign rules. Positive over positive is positive. So we know that the function is above the x-axis in this area, right? Well, what can it be doing then? There's only one thing it can do, isn't there? I mean, I guess that when we get to calculus, we can tell for sure that there's only one thing it's doing. It's possible at this point, we don't really know. I mean, we can't be as specific now as we can in a couple of years. I guess it's possible maybe that this function, we might think this function is doing something like this. Maybe it's going and then going up. I mean, we don't know that kind of stuff. We don't know if it's got some peaks and valleys in there that we're just not finding. But I'm picking functions that aren't real complicated like that, so we don't have to worry about that stuff. In calculus, it'll be easy for us to find any of those places too. But for us, if we know it's a pretty simple function, and there's no x-intercepts over here, and we know that it's above the x-axis, and we know it has to stick to those asymptotes, that's the only thing it can do, isn't it?
Yeah.
Right? It's got to just sweep from this asymptote up to that asymptote, right? Now, what about between negative 2 and positive 5? If we pick 0, that's an easy one to check, and we did that last week. If we plug 0 in, we ended up getting a negative value for our function. And we checked the signs of all the factors. So that means it's below the x-axis. Okay, when we check 10, which is above our hole, we also get negative. So what's that mean? It can only be doing this kind of a thing, right? There's no x-intercepts, and it's always negative. It's got to stick to these asymptotes. So that's really the only thing it can do.
If it's zero or if it's negative at zero, you don't even have to check the element, right?
Okay, well, we don't, if we really think hard about this, we don't. But there's one possibility, and that is, what if our hole is actually on the x-axis? Then it could, you see what I'm saying? Then that could change things a little bit, right? But by checking a value to the right of our hole and seeing that that's still negative, it has to do that, right? Because there are no x-intercepts, and so this thing has no, other than where it's separated by a vertical asymptote, there's no way for this function to ever jump up above the x-axis without going through the x-axis, right? So it's got to look like this, okay? We looked at another one, a little simpler one. We looked at one like this, where there were no zeros, no real zeros of the denominator, right? So no excluded values of x. The top is 0 when x is 0, right? So we got one x-intercept at x equals 0, and if we plug 0 into our function, we get 0, 0, right? And so this was a pretty simple one, right? We know that there's no vertical asymptotes. We checked the horizontal asymptotes by taking a limit as we approach positive or negative infinity. And so if we look at the ratio of the leading terms, I get the limit of 5x squared over x squared. Well, the x squareds cancel, and I just get 5. Right? So the horizontal asymptote, our limit, as we go out to the tails of the function at positive or negative infinity, is 5. And so we get the horizontal asymptote is just the line y equals 5, right? We have one x-intercept, which is at 0. So really, this is pretty simple. All we got to do is just check a value of the function to the left of 0 and the right of 0. So if we just pick like a test point at -1, for example, if I plug that into my function, well, look, I get something positive, don't I? Right? Because all the x squares, all the x's are being squared. If I plug in +1, I get positive. So what's the only way that that could happen? Now think about this. If it's touches the x-axis at 0, but it's above the x-axis everywhere else, and it's got to stick to this asymptote, isn't it just doing that? Right? You get the idea? Okay? And then the last one we looked at was a little tougher, right? This one was a little harder to factor. Bottom was easy. Bottom factored into x plus 4 times x minus 2. So we know we've got to exclude the values -4 and +2. But we got to know what the top factors into to determine are those holes or asymptotes, right? So we did that. We looked over, the top is a 4th degree, or is a 3rd degree polynomial. We got 4 terms. Grouping doesn't work because the ratio of 2 to 10 is different than the ratio of -16 to -24, so we can't group. We had no choice but to use the rational root theorem and just make a list of possible zeros and start checking. And we already did some of that work. We found that, what did we find here? We found that -4 worked, didn't we? Okay, when we plugged -4 in, it worked. What did we do?
Oh, remember you thought it didn't work, it didn't work. And then you
Was
said-
it was 2 that worked, wasn't it? Yeah, 2 worked. I don't know why do I have a, oh, I know what I was doing. We were gonna, I got it. So yeah, we tried 2, and 2 worked. 2 gave us a 0, right? So we know that x minus 2 is a factor, okay? Well then what was left over? When I plugged 2 in, these were the coefficients that were left over. 2, 14, 12, right? So we know that x minus 2 is being multiplied by 2x squared plus 14x plus 12, right? And then that was our remainder was 0. So we could factor a 2 out of that. If we undistribute a 2, we just get x squared plus 7x plus 6, and that factors pretty easily, doesn't it? Right? So once we found 1, 0, the rest was pretty simple, right? Because then we're left with a quadratic, and that's no big deal. So we got this thing all factored, the numerator of our polynomial, And if we go back, oops. We got that in the wrong spot. Okay, so there it is. So now that we know what the numerator factors into, we can determine what's going on in each of those places. So what about x equals -4? Is that a shared zero or is that a unique zero of the bottom? A unique zero of the bottom, so what must be happening at -4? No, if it's a unique zero, it's got to be a vertical asymptote. So at 4, we've got a vertical, or -4, we've got a vertical asymptote. So we add that to our function. There's a vertical asymptote, right? At +2 is a shared zero, so +2 is a whole. So we get a whole at x equals 2. Okay? All right, what about, so that gave us the vertical asymptote. Now, what about the end behavior? This was the part where we kind of got stuck at the end a little bit, right? And this is where we sort of ran out of time. So to find the end behavior, we're going to take the limit of the function as x approaches plus or minus infinity. All we need are the leading terms, so we just get 2x cubed divided by x squared. Now that simplifies to 2x over 1, doesn't it, right? Well, as x approaches positive infinity, that's going to be positive infinity, isn't it? Right? So out here, when we take the limit of the function as x approaches infinity, we know that this function is going to be positive infinity. In other words, if I go to the left forever, I'm going to go up forever, right? What about if I approach negative infinity? If I take the limit as x approaches negative infinity, well, what's the limit of 2 times x as x approaches negative infinity? Negative infinity, right? Because I'm going to get +2 times a huge negative number, which is a huge negative number. So the limit as x approaches negative infinity is negative infinity. It's going down forever to the left. Okay, but there was one other thing we could do here. We noticed that because the top polynomial is 1 degree bigger than the bottom polynomial, this gives us a special circumstance where we can find what's called a slant asymptote that really helps us out. And we get that by just dividing it out and simplifying the quotient. So if I divide the top by the bottom using long division, look what happens. If we just go through the process, we get 2x plus 6 plus the remainder of -12x plus 24 divided by our denominator. The remainder is what remains over the denominator. Okay? And so now look what happens when we take this limit. If we take the limit, I want to redo this part. So we've got f of x equals 2x plus 6 plus what remains over our denominator. What remains over our denominator was this -12x plus 24. So if I take the limit of my function then, as we approach plus or minus infinity, I'm taking the limit of 2x plus 6 plus -12x plus 24, all divided by x squared plus 2x minus 8. I'm taking the limit of that whole thing, right? So that part looks fine. This is just another rational function, isn't it?
Yep.
Right? Now, this is a rational function. That's really similar to one of the previous examples we looked at. That's really similar to
Where it approaches 0.
the very first example, isn't it? Right? We looked at this first example and we found that
4 over x.
we had -4x over x squared, right? Now, when we took that limit and we simplified that, because the bottom was a bigger power of x than the top, we ended up with an x left over on the bottom and nothing on the top. And when we took that limit, it went to 0, right? Because the bottom was exploding faster than the top of the fraction. Isn't that what's gonna happen here too,
Same exact thing,
right? It is, it's the same thing.
except about 3 times less.
So if we look at this limit as x approaches plus or minus infinity, because the ratio of those leading terms, because the bottom is a bigger power of x, when we take this limit, that whole part is gonna go to 0, it's gonna disappear, right? And what we're left with is just this. Okay, what's that equation of? Line. Okay, so the asymptote in this case, when we take the limit as x approaches plus or minus infinity, all the remainder part just goes to 0, and we're just stuck with a line instead. So that is what we call a slant asymptote.
Slant.
Because it's an asymptote, but it's not horizontal and it's not vertical. So if we go back and look at a picture of this thing,
There it is.
there's our slant asymptote. The equation of that line is just y equals wasn't it 2x plus, what was it, 2x plus 6?
Uh-huh. You can see the 6 there.
So there's our, yeah, it goes from 6 to, there you go. So there's the equation of our line, and we can see that on a large scale, the function's gonna have to stick to this asymptote, clear off to the left, and clear off to the right. Okay, we only had, how many x-intercepts? I think, well, then we ended up with x-intercepts at -6 and -1, because those were unique zeros at the top, right? Places where the top is 0 and the bottom is not. So at -6, y is 0, at -1, y is 0. So look at all these places then. We gotta pick test points that are outside of and in between are zeros and all of the places where we have to exclude x values, so the asymptotes and the holes. So we've got important things going on at -6, -4, -1, and 2. So we gotta pick test values, we gotta pick 1, 2, 3, 4, 5 test values surrounding those to see if the function is above or below the x-axis, right? And we did that. When we plugged -10 into our function and we found out what the signs of all the factors were, the overall result was negative. At -5 it was positive, at -2 it was negative, at 0 it was positive, and at 4 it was positive. And so if we look at the function then, and that kind of summarizes that behavior, right? Out here to the left of this point it was positive, it was negative, it was negative, it was positive, it was positive. So our function can only really do one thing then, can it? Right? It's passing through the x-axis here and here, right? And it's got to connect to these asymptotes. So if I were to go further out there, this thing would just kind of sweep down and kind of approach that slanted line, right? As it sweeps closer to this vertical asymptote, it's just going to get pushed up to infinity, right? Over here on this side, when the function, if I were to go to the left, getting closer to this vertical asymptote, it's just going to get pushed down to -infinity, right? It passes through the x-axis. As we move on to the right, it travels through that hole, but it's going to kind of get squeezed up onto that slant asymptote.
Through the whole thing, it goes kind of by.
Well, it goes, you're right, I mean, the hole it interrupts the function, right? Okay, that make sense?
So it's not really a hole, it's kind of like a.
No, it is. It's what we call a hole because it's just one point missing. There's
like
just
a-
one point
It's
missing.
like it's a line. It goes up there.
It's a point.
It's a point-sized hole in the
But if
function.
you move that line, like if you change other things to change the dynamics of that line, the hole would still be at where x is 2. What? It's not a point. So I mean, it ends up being a point because that's where the line is, but the hole is not really a point.
If you move the line, if you move the line up, the hole would go.
Oh, yeah,
It would.
He's on
That's
something.
just at
Yeah.
2.
No,
So it shouldn't be called a
he's
hole.
not.
He's on something. It should be called a slash.
Well, you talk to all the mathematicians to see if we can't get
Yeah,
that
I think
fixed.
they're fucking dumb.
So here's the kind of stuff I want you to be able to answer on the assignment though. You're gonna have to be able to fill in all these blanks. Are there any vertical asymptotes? No. In this case, what's the domain? The only values we had to exclude were 2 and -4. Are there any holes? Yeah. Where, at what x values? Were there any horizontal asymptotes? Well, actually there was a vertical asymptote. It was, I can't remember where it was, but we had one. It was at x equals -4, I think it was, right? So we had a vertical asymptote at x equals -4. We had a hole at x equals 2. Okay, listen, I know it's probably masked up, but you can't get off track on this part. You got to really just maintain your focus for a second. Yep.
So the horizontal asymptote is, it's a slope, not really.
Yeah, so it's not a horizontal asymptote. It's a slant asymptote. And that was at y equals 2x plus 6. And then everything else we just get from our table by just knowing, between all these places is the function positive or negative, above or below the x-axis. And by knowing those clues, you kind of have to just be a detective and put the shape of the function together. Yes, sir.
How would you submit a slant test?
You'd write the equation of it. That's what you do. You just write the equation of the slant asymptote.
Of course.
In the horizontal
So I don't know if I have an example of a question like that up here, but I'll put one up. It says, there's a box that says, I'll pull one up in a second, we'll see. I can't remember. Okay, here's some stuff though. Let me get you back on track here for a second, please. So here's some stuff we want to be able to come up with. You probably saw this trend. We looked at 3 different examples. What's always the case, if the numerator is a smaller degree than the denominator, so the polynomial in the denominator has a bigger power of x than the numerator, what is their end behavior result?
The numerator is the top right.
So that was this case right here, right?
You get bigger.
It goes to infinity.
So, well, no. As x goes to positive or negative infinity, what does y do? Right? We want to take the limit. What's the limit of the ratio of the leading terms if the bottom is a higher power of x than the top? What happens? 0. It's always going to be 0, right? From this point forward, you don't even have to think about that. You just know that if you see that pattern, you're going to get 0, y equals 0 is going to be your horizontal asymptote, right? So if the bottom is a higher degree polynomial than the top in a rational function, no, numerator is smaller degree than the denominator. Okay, then you get the horizontal asymptote. The horizontal asymptote is going to be y equals 0 every time.
It's also going up and down. So what do you say about that?
We don't care about that. All we're asking about here is the end behavior.
But that would be somewhat of it. Or is that not an end behavior because it's going in towards each other?
I guess I don't understand your question, but when we talk about end behavior, when we talk about end behavior, all we care about is, that's not end behavior.
That's middle behavior.
That's behavior at finite values of x, right?
Oh.
End behavior is at infinite values of x, positive or negative infinity. So we just care about
Oh,
really
I
far to the
see.
right or really far to the left.
That makes sense.
So that's different. That's a vertical asymptote.
I know you.
Okay, what about the next case?
That's the negative.
What if the numerator is the same degree as the denominator? That was our second example. Right there, what did we find? Okay, and we got the answer 5. Could we have seen the answer 5 without even taking the limit?
Yeah.
Where?
Coefficient of
Ah.
same power.
Okay, all we did was we just took the ratio of the leading coefficients, right? Because we're taking the ratio of the leading terms, and the x's are going to cancel when we take the limit. So all we got to do is look at the ratio of the leading coefficients, and that's going to be the value of our limit. So y equals that is our horizontal asymptote, right? So let's put that in our...
So the end behavior is 5.
So in this case, if they're the same degree, we get a horizontal asymptote, and y is just equal to the ratio of
Leading coefficients.
the leading coefficients every time. And then what if the numerator is of greater degree than the denominator? If the numerator is of greater degree than the denominator, there is no horizontal asymptote.
Oh,
Right? There's no horizontal asymptote.
Why?
if they're the same, there's going to be a number.
So, we know that we're going to get infinite behavior at the, at the tails of the function. It's going to have to be infinite. But if we get one special case, if the numerator is exactly 1 degree higher than the denominator, when I divide those polynomials out, I know I'm going to get a line left over. I'm going to get a linear equation plus some remainder, right? So we get one special case here. If the degree of the numerator is exactly 1 greater than the degree of the denominator, then that tells us that we're going to get a slant asymptote.
We need to get a better name for that.
Okay, now this wouldn't work. Like if the numerator were 2 or more degrees bigger than the denominator, then we don't get a slant asymptote, right? Then we know that we're going to get infinite behavior at the tails, but it's not going to follow this nice asymptote. Okay.
Wait, so what's gonna happen?
So, we'll look at an example here, and I'll show you. I'll show you one quick example of
That's
that.
good. Quick.
But what do we do? If we have a slant asymptote, then all we have to do is just divide out the polynomials and ignore the remainder, right? So when we divide the polynomials and ignore the remainder, that gives us the equation of the slant asymptote, right? Okay? If you know that stuff, you know how to do this. Here's the other kinds of questions you're going to get
How did we?
are like
find-
this.
So, how did we find the horizontal asymptote of 5?
Because we took the ratio of the leading coefficients,
Oh,
right? We had 5x squared over x squared,
oh, that's
over
when
1x squared.
That's when they're saying 3.
Yeah.
Oh, I feel it.
Okay, so what about something like that?
So it's gonna be, I don't know, that's gonna be a slant asymptote.
You see what it's asking for? It wants, like, I'm going to give you some questions like this where they're going to ask for 4 things. Now, you don't have to do a ton of work on this, right? You have to do a little bit. But we know that the domain has to exclude 3, right? So the answer to the first part would just be, I should probably change these so we don't have to put the not equal to sign. I will, right? But for now, you got to put the not equal to sign in there.
Aw.
I'll change them so you can just put the x values. So we do x is not equal to, what was it? Negative 3.
Negative 3.
Okay, so that's the value that has to be excluded. Write the equation of any vertical asymptotes. Well, if we factor the top of this thing, we just need to see is negative 3 a 0 of the top, right? Well, we can check. If I plug negative 3 into the top, I'm going to get negative 3 times 9 minus 9 times negative 3. So we're going to end up getting 0, aren't we?
Yes, we are.
Right? Negative 27, yeah. Yeah. So because negative 3 is a simultaneous 0,
Wait, maybe not, though. Yeah, we are. Yeah,
Right.
we are. Yeah, we are.
so that we're not going to get a vertical asymptote in this case. So we would just put in, right? Because the 1, 0 of the denominator is a whole. Right? So it occurs at x equals 3.
A whole is a shared 0, I thought.
0 is an x-intercept, isn't it? Right? Does it ask for those? I don't think it asks for those. I don't ask for any of those. Now, the function has a horizontal or a slant asymptote at where? So we're supposed to write the equation of the asymptote. Okay? So if it's a horizontal line, it's just going to say like y equals 5, for example. But if it's a slant asymptote, we'd have to actually divide this out and see what we get. Well, in this case, what's that look like? We've got, this is a much easier division problem, isn't it? So look what we get. We have a linear denominator, so instead of having to use long division, we could just use synthetic division. Right? If I want to find out, we're trying to find out what's the equation of the slant asymptote. I just have to simplify this quotient, divide it out. So I can do this synthetically. What goes out front?
Negative 3. I'll take negative.
What are my coefficients?
Negative 3. Negative 9. 0.
And if I do my synthetic division, I'm gonna bring down the -3, I'm gonna get 9, that's a 0. And I get, in this case, I get 0. So I do get 0 remainder. But either way, if I have a remainder or not, this is gonna be the equation of my slant asymptote right here. I get -3x plus 0. So my slant asymptote is y equals -3x. Right, so that's all I would put down here,
That's a pretty satisfying one.
right? Okay, make sense? Okay. All right, so you got 5, that's the last assignment. Yeah, I'm almost done building the test and the practice test. So I will give you this now. This test, we're gonna just do one test over this section. It's gonna have, I think it's gonna have like 10 or 11 questions. I purposely didn't, I made this one like not so hard. I mean, you'll see, when you look through the practice test, and this one it doesn't have as much stuff on it, right? It's really not there's a little bit of graphic stuff, you gotta solve some equations. You gotta add or subtract one time, multiply or divide one time on the test.
How about you don't put that one in the grade book?
No, it's going in the grade book.
I have melanoma.